So I give the lecture instead of him this week. My name is Shuping Huang. And first, I'd like to make a brief self-introduction. I'm from China, and I obtained my PhD degree in 2008 from Fujian Institute of Research on Structural Matter, which is one of institutes of Chinese Academy of Sciences. After I obtained my PhD degree, I went to City University of Hong Kong and worked as a research fellow for 2 years. And after that, I went to Kyushu University in Japan, also as a postdoc fellow for 2 years and 2 months. Now I'm a postdoc researcher in Dr. Killing's group. Today I have no materials to hand out, and we have no homework, but please start working on projects. Next lab time is April 16th, next Tuesday. It's about TDDFT and doing projects. The project is about the law of heat. We will study how the heating will modify the electronic properties of materials. First, you should select models and then optimize a geometry. And after the geometry optimization, you can do density of space calculation and calculate a spectrum. On the other hand, you can do heating and molecular dynamics. After molecular dynamics, you study the density of space and compare the density of space and spectrum, both doing molecular dynamics and after doing molecular dynamics. Next presentation time is April 25th. You will do projects. And Dr. Killing might have provided a list of subjects. You can choose one of the subjects and start to prepare plan of research. In the last lecture, we have practiced the skills on mass software, and in this lecture, the goal of this lecture is to use principle of time-dependent density functional theory to describe excited space. We will focus on the procedure of constructing density out of pairs of orbitals. Here shows the plan for today's lecture. First, we will make a brief review of density functional theory, and then explain why we need excited space. And finally, we will focus on non-equilibrium density. As we remember, the central idea in DFT is there is a relationship between the total energy and the electronic density. Most of DFT software use constant equation. In constant calculation, first we give a initial density for a structure model. Use this kind of thing. this. Oh. Hmm? PowerPoint. Oh, okay. Thank you. Wait, okay. Thank you. First, we provide a initial density, and we can use this density to calculate the case potential. Uh, Case potential have different components, and it was calculated separately, and each one poses a different numeric problem. After we obtain the case potential, we solve the case one electron case equation. The goal of to solve the case equation is to find the lowest eigenstate of case Hamiltonian, and after the summation of the equation, we have all the integrands to obtain the new density. If the convergence criterion was reached, the calculation is finished. If the convergence criterion is reached, the self-consistent cycle is stopped. If it's not fulfilled, we should restart the self-consistent cycle with a new density. The case equation can produce the ground state structure, electronic density, and atomic structure and lattice constants. It has some problem in predict the band gap generally and estimate the band gap, and also has some problem in to quantitatively and sometimes qualitatively to predict the absorption spectra. In this absorption spectra is related to excited state properties. Here we will study what are excited states. Excited states is a state of any quantum system which has a higher energy than ground state. If the system is perturbed by electric field or optical field, such as a photon, the molecule will absorb the photon to produce an electronically excited state. And produce over here. After excitation, the electron might undergo deactivation by emit photon to reform ground state. Here shows the different electronic configurations. This one is ground state electronic configuration. If one electron is excited to unoccupied orbitals, is singly excited configuration. This one is one electron is excited from HOMO to NUMO. And this one is excited from HOMO to NUMO plus 1. If two electrons are excited, it corresponds to doubly excited configuration. In order to predict UV-based electronic spectroscopy and to explore the problems in photochemistry and photophysics, theoretically we need to treat the excited states. Here are some sentences taken from review of calculation of excited states. Knowledge about the energetic position of electronic excited states relative to the ground state, as well as information about the geometric and electronic properties of excited states, is necessary for the exploration and interpretation of electronic spectra of molecular systems. And sometimes a ground state method can be picked to calculate a particular electronic excited state if the ground state formalism can be forced to converge onto the energetically higher solution by introduction of constraints. These constraints may be given, for example, as a different spin multiplicity. Here one can use a ground state method to calculate the ground state of every possible spin multiplicity. For example, if the ground state is the spin multiplicity of the ground state is 1, we can change it to 3 to study the triplet excited state. But if we want to study the singlet excited state, the DFT has problem. So we should develop new approaches to calculate excited states. Several quantum chemical approaches for the calculation of excited states are available that do not require any priori constraints and can produce energies and oscillator strengths of several excited states in one single calculation. And TDDFT, dependent density functional theory, is one of the most widely used methods. It can be applicable to model and large systems. Electrons are particles with half integral spin, and which must obey Pauli exclusion principle. And Fermi-Dirac distribution applies to electrons. So we can write the density in such a form. It's the sum of a set of one electron orbital times Fermi weight. F is Fermi weight. It has a distribution like this. So we can artificially perturb the Fermi weight in order to approximately treat excited states. And the density can also be write such a form. So Ij is density matrix. Weight density matrix. Density matrix is a matrix that describes a quantum system in a mixed state. It's a statistical ensemble of several quantum states in contrast to a pure state, which is described by a single state vector. Suppose a quantum system may be found in state 1 with probability P1, or it may be found in state theta 2 with probability P2, or it may be found in state theta 3 with probability P3, and so on. The density matrix for this system can be written as these forms. The expectation value for any observable A is given by this form is the summation of the expectation value of A for each pure state, weighted by the probability P. And the density can be decomposed into 4 components. The fourth complement is ground state density. G is ground state. Excited state. And the ground state density is equal to delta function times Fermi distribution, and is approximately equal to delta function. It's 0 for unoccupied orbitals and is 1 for occupied orbitals. The second term is the density for the transition from ground state to excited state. And the third component is the density for excited state to ground state transition. These two terms correspond to transition density. And the fourth component is excited population density. The ground state density matrix is assumed to describe non-excited atomic models and is always big. The total density can be approximately equal to the ground state density. And the additions to the ground state density are small. Low EG is smaller than low GG, and low GE smaller than low GG. And low EE is far smaller than ground state density. Any additions to ground state density are perturbative. They are small and proportional to the perturbing factor, such as the strength of electric field times dipole moment. And so we can write the total density in terms of electric field. The ground state density is almost the same as in absence of perturbation, and the transition density is small, and for the excited state population density is even small. When the perturbation is weak and the dipole moment times electric field is smaller than 1, then it's larger than its square. So we only need to consider inherent terms and develop an equation of motion for them and apply the density functional theory for them. How to treat perturbational density in a numeric way? Both density matrix low GE and low EG are matrices. How to save them in a numeric form? The total density can be expressed in a form of pairs of orbitals. The pairs of occupied orbitals this is corresponding ground state density. And the pairs of occupied and unoccupied orbitals correspond to the density matrix for ground state to excited state. And the pair of occupied orbitals is corresponding to OEC.
Excuse me. Yeah. Why is that double notation in the like homo minus one, homo minus one? Why not just homo minus one?
This is homo minus one, homo minus one, homo minus one, homo.
What does that signify?
Sorry, can you repeat the question?
Is that density?
Yes, then is density.
Density between homo and homo minus one, something like that.
Is low. Is the electron the probability of electron state at homo orbital.
Okay. Thank you.
And the pair of unoccupied orbital is excited state density. This is just an example of the density matrix near the band gap. If we want to treat more excited state, and more pairs of orbitals should be included in this matrix. Here, only 4 components of the for each component are shown with minimal energies. What is perturbation density matrix? Perturbation density matrix can be expressed as correlations to ground state density. The ground state density, which can be obtained by time-independent DFT. In order to treat the problems related to time-dependent fields, such as the many problems in molecular optics and spectrum, TDDFT is needed. So in order to solve the eigenvalue problem in TDDFT, we organize the transition density in form of pseudo vector form. So this is the density matrix for ground state to excited state transition. And we can add each row in the matrix form and to build a super row column. And this is a pseudo vector which contains the element of a matrix. So for the excited to ground state transition density. Back please. One. Normal +1 to normal -1 transition. Normal. And the perturbation part of density matrix is often stored in a form of vector. Log G we can stored in X vector, and rho EG is stored in vector Y. In the ground state density, rho GG is assumed to be unturbed, and excited state population density rho EE is assumed negligible. So in TDDFT, this part is not included. And what would be the x and y vectors for the first excited state? And what is the first excited state? Electron is excited from HOMO to NUMO. So if we didn't consider electron and hole interaction, only this component is equal to 1, and all other elements are 0. How about the low EG? For the absorption is referred to the electron is promoted to HOMO to LUMO. All the components are zero. If we consider the emission, the electron undergo the activation from LUMO to HOMO and to deform a ground state. This low LUHO is equal to 1 and other elements are 0. So in order to describe excited states, we have to build an equation for pseudo vector x and y. And in the next lecture, we will study how to build an equation for pseudo vector x and y. Is there any questions? If there is no question, today's lecture is finished.
Excuse me, can we ask you about the projects that Dr. Kilin has given us? Can you help us on that?
Projects.
Yeah. I just wanted to ask you a few questions.
This is
No, class projects.
No, our project, individual project we're talking about.
Like the lab, about the labs.
About next lab.
Okay.
I would say email him and let him tell you what you need to do with those, because he's going to be, I think he's got access to email where he's at. He's at a conference, so send him an email and he'll get back to you.
Oh, okay. Thank you.
Okay, thank you.
If we are done with class, maybe I can ask with some of our friends over there. Actually, I wanted to contact with Stephanie.
Can you repeat?
Are we done with our class?
you done?
Yes.
Yeah.
Okay.
Yeah.
Dr. Killian was saying that Stephanie has done some work on TiO2. You have built some models.
Yeah.
If we can use that model for further optimization of ours, can you provide us your model?
Yeah, I can. Do you just want, I'll move it to a directory in the Keeling lab, what we work under. And
Okay.
like, was there a specific doped one you wanted, or does it not matter?
Undoped one. What
The
you have
undoped-
used for doping?
About 13 transition metals.
Oh, okay.
So,
Maybe one or two of doped and undoped one as well.
Okay, and then if you move it, just open it up in JMOL, and you can dope with any element, so it's pretty easy
Okay.
with the replacing. So actually, if I just do the undoped one, you can do any doping you want with it.
And for doping, how we do? We do it on like Gauss view, and then how we do that?
Yeah, so I think I can turn it into an XYZ file for you. When I did it, I was doing it in JMOL, but I think with a simple transition, we can make it into Gauss view. And then I did surface doping, so you can either do in the slab or out of the slab.
Okay. I
so
also
you
have
just
to do like
delete-
surface doping.
Yeah, you just delete a titanium atom and replace it with your dopant, basically.
Oh, okay.
So I'll move that to a directory. I'll just put undoped.
Okay.
It'll
Thank
be
you. Thank you.
TI-32 with a bunch of other stuff.
Okay. Thank you. Thank you. Thank you for class. Thanks.